Hello everyone. We start with this week's new chapter, which is routing in switched data networks. This is actually chapter 19 in your book. So let's start with this chapter. What is routing and what are the different ways of selecting a route? So the primary function of the packet switching, if we can recall, we studied about packet switching and circuit switching in the previous chapter. So the main function of the packet switching network is to accept the packets from the sender and deliver it to the receiver. So to accomplish this task, a path or a route must be established through the network, and generally there is more than one route is possible. So a routing function has to be performed. For example, let's talk about in general what is routing. Suppose you want to go from Saudi Arabia to the United States. You have many options available, you have many ways available, right? So what will be your criteria? Suppose you have the flights available, direct flight available to the US, and you have like you can go with a break journey also. So you have the options. Now it is up to you which route do you select. Suppose you can take a flight from here to Turkey, then from Turkey to UK, and then from UK to US. Or you can take a direct flight from Saudi Arabia to US. So there can be other routes also which are available between Saudi Arabia and US. But you are going to select a particular route based on some criteria. For example, cost, the minimum air ticket cost. So whatever flight will or whatever route will give you the minimum air cost, you are going to take that route. So for example, if breaking your journey into different stations or in different countries gives you the least cost, for example it gives you maybe 2000 or 4000 riyals, you are going to select that route, although it will take more time to reach to US rather than taking a direct flight. So the same thing is applicable to the internet also, in the packet switching also, because there may be many routes or many paths available between the sender and the destination. So one of the best possible path has to be selected between the source and the destination to send the packets or to send the message. So routing is the primary function of a packet switching network. To accomplish this, a path or the route across the network between the nodes have to be selected. Now, when we select a path, when the path has to be selected, what are the characteristics required from that path? So, the following are the characteristics that are required from the path. The path should be correct, simplicity, although I am going to explain all these in detail. So the characteristics of selecting a path between two stations or between sender and receiver are correctness, simplicity, robustness, stability. Robustness is to overcome the failures. Stability, react to the changing condition. For example, if a node fails, then fairness, optimality and efficiency. So let's talk about all these things in detail. So the first two items, which are simplicity and correctness, they are self-explanatory. For example, the route should be correct. So if I am sending the message from, for example, A to B, this path should be correct. It should not lead to somewhere else. The path should lead to the destination B. Second is simplicity. It should be a very simple path, not a complicated path. For example, going from here, then here, then here, it's quite complicated. The path should be very simple also. Third is robustness. Robustness means the ability to overcome failure or overload. So for example, if a packet is traveling in the network, suddenly there occurs a congestion in the network. So that path should be able to tolerate the overload or tolerate the failure. So robustness has to do with the ability of the network to deliver the packets with some route in the face of the localized failures and the overloads. Ideally, the network can react to such delays without the loss of packets or breaking the virtual circuit. Alright, so the next is stability. Stability means react to changing the condition. So robustness and stability are also related. So if a path is able to tolerate the robustness, it should also be able to maybe a stable path. So techniques that react to changing the condition, they have unfortunate tendency to either react too slowly or too fast for the unstable swings. For example, a network may react to congestion in one area, whereas in the second area, if it is overloaded, it may not be able to react. So stability is also one of the important characteristics. Next, we come to two important factors, which are fairness and optimality. Fairness means loads between nearby and distant stations, and optimality means seeking the optimal solution. So a trade-off also exists between these 2 points. Some performance criteria may give high priority to the exchange of packets between the nearby stations as compared to the exchange of distant stations. So sometimes it may happen that some routes may give, for example, if the packet has to be sent to a station which is quite nearby, so priority will be given to that packet, and if a packet has to be sent to the station which is far off, it may be given a less priority. So this policy can maximize average throughput, but it will appear sometimes unfair to the stations which are normally far off. And the last characteristic which is desired is the efficiency. Efficiency is less processing and transmission overheads at each node. So because some processing overhead at each node is involved and the transmission overhead is also involved, so the penalty of such overhead need to be less than the benefit obtained. So these are some of the characteristics which are required while selecting a route. So moving ahead, next we come to the performance criteria. What should be the performance criteria? So let's talk about the performance criteria. Alright, let me just go to the next slide first of all. Alright, these are some of the elements of routing techniques for packet switching networks. So in elements of techniques under packet switching networks, we have many different categories. First one is the performance criteria, then we have decision time, then we have decision place, network information source, and network information update timing. So all of these elements we are going to discuss. So the first thing is the performance criteria. Under performance criteria, we have number of hops, cost, delay, and throughput. Now what is it we are going to discuss? So performance criteria is used for selecting a particular path or selecting a particular route. So the simplest way to choose is the minimum hop. Minimum hop means minimum number of nodes between the sender and the receiver. But instead of minimum hop, it can be generalized as a least cost routing also, because we may be interested not in selecting the minimum hop but in selecting the least cost routing, because least cost is more flexible and more common than the minimum hop. Let's understand what is this minimum hop and what is this least cost from our general way of example. So for example, I'll take the same example. You want to travel from Saudi to US. You have three options. The first option is to take a direct flight to US. Second option is go from Saudi to Turkey, and then from Turkey you take a flight, direct flight to US. The third option is, this one is the first option, this is the second option, and this is the third option. Third option is from Saudi you go to Turkey, then from Turkey you go to UK maybe, then from UK you go to US. Now if you see, if I go with minimum number of hops, my first choice does not have any stoppage in between, so that should be ideally my choice. But let's assume that the cost of taking the first option is maybe 10,000 Saudi riyals. The cost of taking the second option may be 8,000 Saudi Riyals, the air ticket, and the third option may be it comes as 5,000 Saudi Riyals. Alright, now I have to select my criteria, whether to go with minimum number of hops or the least cost. Mostly least cost is preferable as compared to the minimum hop. So if you see over here in the first choice, I have a direct flight to US. I don't have to stop in between. So I don't have a lag or I don't have to stop in between. My second choice is I have to stop at Turkey. Then from Turkey I have to take a flight to US. So I have only one hop over here. But in the third option, I will stop at Turkey, I will stop at UK, then I will go to US. So that means I have two hops. If my strategy is to choose minimum number of hops, of course, my choice should be one. But normally, we don't go with minimum number of hops, rather we go with the least cost. Because least cost is more flexible and more common than minimum hop. Again, in your daily life also, you are not going to count the hops. Rather, you will go with the minimum or the least cost. So, the third option is costing you the least, although it has maximum number of hops. So, same thing goes with the selecting the route or the path criteria when it comes to the network. So this is the difference between the minimum hop and the least cost. And least cost is more flexible and more preferable than the minimum hop. Alright, so number of hops, cost, delay and throughput. So the selection of a route is based on some performance criteria, and the simplest criteria is to choose the minimum hop route. That means it passes through the least number of nodes through the network. So this can be easily measured criteria and can minimize the consumption of the network resources also. But a generalization of the minimum hop is the least cost routing. In this case, a cost is associated with each link for any pair of attached stations. So the route through the network accumulates, the least cost is sought. Now cost is assigned to the links to support one or more objectives, and cost can be inversely related to the data rate also. Okay, so let's understand more by going to the next slide. For example, this is an example of nodes connected in the network. Now each link, for example, N1 is connected to N2. Now this link has a cost of 2. When I want to grow from N2 to N1, it has a cost of 3. For example, now if you see the numbers written on the link, they define the cost, and the one written in the circle, they are the nodes. So for example, if I want to go from N1 to N4, the link cost is 1. If I want to go from N1 to N3, there is a cost of 5. But there are other alternative paths also. For example, I can go from N1 to N3 directly by taking this path. I can go from N1 to N4 and then from N4 to N3 by taking this path. Or I can go from N1, N4, N5 and N3. So there are multiple paths. The one that I have to select is minimum hop or the least cost. So let's take up this example. So this is a figure. It's a 2-arrowed figure. Now for example, from N1, if I want to go to N6, right? If I want to go to N6, let's assume that my first criteria is minimum hop. So the minimum hop means least number of stations. Going to N6, I can go from N1 to N2, N2 to N3, then N6. How many hops I have? 1 and 2 hops. I can go from N1 to N4, N4 to N5, N5 to N6. Again, how many hops in between I have? 2 hops. But my criteria is minimum number of hops. So I can go from N1 to N3 directly and then from N3 to N6. So that means from node 1 to node 3 and then to node 6. So this is the minimum hop because I just have only one hop in between. But what is the cost for selecting this route? Let's check the cost. Going from N1 to N3 is the cost of the link is 5. Going from N1 to N3, the cost of the link is 5. Then going from N3 to N6, this cost is also 5. So 5 plus 5 is 10. This is the cost when I select the minimum number of hops. Now I can, instead of selecting minimum number of hops, if I select the least cost, the path that give me the minimum possible cost, although I don't mind, I have to travel many number of hops, I don't mind it, but my aim is to have the least cost path now. So what can be the other? For example, I can select a path from N1 to N4, N4 to N3, N3 to N6. So but the cost is again N1 to N4 is 1, 1 plus 3 is 4, 4 plus 5 is 9. Again, that's the more cost. So I have a route which is better than this route, but this has more hops. For example, N1 to N4, N4 to N5, N5 to N6. So what is this route? From 1 to 4, 4 to 5, and 5 to 6. I have to travel one hop more, but it will give me the least cost. Let's check it. Going from N1 to N4 is cost of the link is 1. Going from N4 to N5, the cost of the link is 1. Going from node 5 to 6, the cost of the link is 2. So the total cost is 4. See, 2 less than my previous route selected. So in the minimum hop, I was getting a cost of 10, but in the minimum cost route, I am getting the minimum cost of 4, but I have to travel one hop extra. So this can be the strategy which can be chosen. So in the first case, the least cost in the first case, the least cost route should provide the highest throughput. It will provide me the highest throughput. But in the second case, this least cost route will provide me the minimum delay. So whatever the algorithm we choose, whether we choose minimum hop or the least cost, the algorithm for determining the optimum route for any pair of stations is straightforward, and the processing time should be about same for other computation, because least cost criteria is more flexible and more common than the minimum hop. Several least cost algorithms are in use, and we are going to cover up in our later chapter. We are going to talk about this. Alright, now going ahead, that was about performance criteria. Now let's talk about decision time and decision place, which are the two most important criteria now. So let's check it. What are they? So decision time is determined by whether the routing decision is made on a packet or a virtual circuit basis. So routing decisions are made on some performance criteria, and they are decision time and the place. Decision time is determined by whether the routing decision is made on a packet or a virtual circuit basis. So when internal operation of the network is datagram, because if we can recall from the previous chapter, packet switching can be accomplished or can be done by two techniques. One is datagram and another one is the virtual circuit. So decision time basically depends on what type of packet switching network we are using, whether we are using datagram or we are using the virtual circuit basis. So when the internal operation of the network is datagram, routing decision will be made individually for each packet. So each packet will have the routing decision made individually. But for the virtual circuit network, routing decision is made at the time when the circuit is established. We have discussed this before in the previous chapter. In the virtual circuit, because the route is established before we actually start sending the data or start sending the information, so the routing decision will be established when the circuit is established. In the simplest case, the subsequent packets using the virtual circuit network, they follow the same route, and the network may be dynamically changing the route assigned to a particular virtual circuit, or it may be a stable. So the route that is established for a virtual circuit network, it can be fixed or it can be dynamically changing. In datagram network, the network may be dynamically changed because the routing depends upon the packets. So all packets are independent to choose their route, because it may depend upon certain conditions like overload or failure of the network. Whereas in virtual circuit network, all the packets using that virtual circuit, they will follow the same route. So going ahead to the next slide, decision place. So the decision place refers to which node or the nodes in the network are responsible for routing the decision, because most common is the distributed routing. This is the most common form of routing. In this distributed routing, what happens? Each node is responsible of selecting an output link for routing the packet as they arrive. So each node has the responsibility to select on which output link the packet should be forwarded to the next hop. It is a complex form of routing, but it is more robust routing. Another form of routing is centralized routing. So maybe it can be a certain chosen node or certain designated node. Maybe it can be a network control center, or for example any chosen node. The danger of this approach is that loss of the network. If that node fails, then it may block the operation of the network. The third form of routing is the source routing. In this case, routing decision is made by the source station. Source station means the sender station, rather than by the network node, and then it is communicated to the network. So this allows the user to dictate a route through the network that meets the criteria of the local user. So let's go to our example to understand these two criteria, decision time and decision place. So this was our network. So for example, decision time and decision place, they are actually independent variables. Now suppose that in this figure, decision place is each node and that the values depicted are the cost at a given instant of time. So we assume that at each node the routing decision takes place, because it may happen the cost may change while a network is established. So for example, if a packet has to be sent from node 1 to node 6, it has to be delivered to node 6. It may follow the path as suggested in our previous example, N1, N4, N5 and N6. Now in each of these, each leg of the route determined locally by the transmitting node. So each node determines or takes the routing decision. Now let's assume that the value changes, such as in between the node 4 or node 5 is no longer the optimum route, or one of the node fails. So in a datagram network, the next packet may follow the different route. For example, node N4 fails, so or node N5 fails when it arrives at N4. So the next packet that arrives, it may not follow this path. It may be transmitted through N3. But in case of virtual circuit network, each node will remember the routing decision that was made when the circuit was established and simply pass on to the packets without making a new decision. So it will simply pass on the packet to this N5, although this link has already been failed, because since this route was established in the beginning, so it will just transmit the packet to the node 5 without being able to know that this link has been failed. So in case of virtual circuit network, the whole operation will fail. Again, the circuit has to be established, or the setup phase has to be established again. So that was about decision time and decision place. Now let's come to the next topic, which is network information source and network update timing. Now most of the routing strategies, they require decisions to be based on the knowledge of the topology of the network that we are using. For example, we may be using the bus network topology, we may be using the star network or mesh network. So some strategies know some information and they manage to get the packets through. There are certain strategies, for example flooding and some random strategies we are going to discuss. They fall in this category. So going ahead, so now we have distributed routing and central routing. So distributed routing, in this the routing decision is made by each node. Individual node may make use of the local information such as the cost of outgoing link. So each node can use the local knowledge, for example cost of outgoing link. Node will collect the information from the adjacent nodes also. For example, this node 1 is connected to node 4 and maybe node 5. So it will collect the information from the adjacent nodes also, and it will collect the information from all other nodes also which may be in that potential route. Whereas in case of central routing, each node typically collects the information from all the nodes. So this is in distributed routing. Each node has a knowledge of itself plus the local knowledge from the adjacent node, and it will collect the knowledge from the other nodes also. Whereas in case of central routing, each node collects the knowledge from the all other nodes. So these are the two basically routing strategies. So going ahead, let's talk about now routing strategies. A large number of routing strategies have been evolved for dealing with routing requirements of the packet switching network. Many of these are also applied to internetworking, but we are going to talk about only these 4 strategies in this chapter. Today in this lecture I am going to cover only the first 3. The adaptive routing will be covered in the next lecture next week. So we are going to talk about today fixed routing, flooding, random routing, and the last one is the adaptive routing, which we are going to talk in our next lecture. Alright, so going ahead with the first strategy of the routing is the fixed routing. As the name suggests, for fixed routing, a single permanent route is established for each source and destination pair, either using least cost algorithm. These routes are fixed, or at least they can only change when there is a change in the topology of the network. So link costs in designing routes cannot be based on any other variable such as traffic, but it can be based expected on the traffic capacity or the traffic capacity. So route is fixed until a change in the network topology. Advantage of using is simplicity. It's quite simple routing strategy. Disadvantage is lack of flexibility. If there are changes in the topology or changes in the network configuration, it cannot handle that. So it's not a flexible. It does not react to the network failure or the congestion. So this is one of the disadvantage of fixed routing. Alright, so let's understand what is this fixed routing. The same example, the same figure as we have learned before is given over here. Now let's understand what is fixed routing. Now we should always remember that it is not necessary to store the complete route for each possible pair. Rather, it is sufficient to know for a network for each pair of nodes the identity of the first node on a route. For example, if you want to go from here to the US, you should know what is your first destination, maybe the Turkey. Then from Turkey you can go to the next route. Alright, so what happens? For example, we want to establish a least cost route from X to Y. From X to Y, maybe from 1 to 6. This is my X and this is my Y. So what are we going to do? So it will begin by X to A link, because from 1 to 6 either I can travel from N1 to N2, from N1 to N4, from direct link, or from N1 to N3. So the direct reachable station I can start from there. So the direct reachable station is from N1 to N2 or N2 to N1 to N4 or N1 to N3. So I will check which of them has a minimum cost. Is it from N1 to N2 has 2, from N1 to N3 has 3, from N1 to N4 has 1. So what I am going to choose? I am going to choose 1. Now this is my, let's assume that X to A. Now my next task is call the remainder of the root as R1. So I have to check what is my remainder of the root. Now from N4, either I can go to N2, either I can go to N3, or I can go to N5. So because this is the way I can reach to N6. So from N4, let's check the cost. From N4 to N3, if I want to go, the cost is 3. If I want to go from N4 to N2, the cost is 2. If I want to go from N4 to N5, the cost is 1. So I have to choose the minimum cost route. So this is 1, this is 1. So that means I am going to choose this route. So now I arrive at N5. So now A to Y. So now next my route has been established over here. So define, so call the remainder of the route as R1, and this is a part of the A to Y. Now we need to define R2 as the least cost route or the algorithm from A to Y. So if the cost of route 1 is greater than the cost of route 2, then the XY route can be improved by using R2 instead. But if the cost of route 1 is less than cost of route 2, then R2 is not a least cost route from A to Y. So we need to have the route which has the minimum cost. Alright. So at each point along the route, we need to know only the identity of the next node and not the entire route. So for example, in our example over here, we need not to know the entire route, rather we need to know what is my next hop station, where should I go. I need not to know the entire route in the beginning, rather I should select from here which is my minimum hop node. So for example, from N1, I can either go to N2 because that is directly connected. I can go to N3 or I can go to N4. So the minimum cost is N4. Now I have arrived at N4. So from here I have to select whether I should go to N2, N3 or N5. Going to N5 gives me a minimum cost. Alright. Now for example, when I arrive at N5, now from here either I can go to N1 or I can go to directly to N6 or I can go directly to N6. Since I have to go to N6, why should, although if you see this has the least cost, right? But I have go to directly to the N6. Why should I go to N3 instead of directly going to N6? So I will choose this cost because this is my destination. So if you see, selecting this path gives me the minimum cost link. Now how does it begins? How the matrix are made? So this is quite important. Now each node maintains a directory for its own. So what happens is this actually suggests how the fixed routing is implemented. So central routing matrix, we have a central routing directory which is created, which is stored at the network control center, and each source and destination pairs also, they also have their own directory. So each node has its own directory, and there is a central directory which is stored at the central directory which is stored at the central station. Alright, so let's now look at how the directory for each node will look like. Suppose from N1 I can go to N2, the cost is 2, the next destination is 2. So what I am going to write is what is my next node, what is my destination and what is my next node. So if I go back from N1 to N2, my destination is N2 and the next node that I have to go to is N2, right? Because from N1 to N2 I don't have any choice. If I take from N4 to N2, it gives me a cost of 3. Now from node 1 to node 3, let's just check and go back. From node 1 to node 3, I can go from N1 to N2 and N3. What is the cost? From N1 to N2 it gives me 2, N2 to N3 it's 5. Or I can go directly from N1 to N3, it's 5 again. Or I can go from N1 to N4. What is the cost? 1. and from n4 to n3 it is the cost 3. 3 plus 1 is 4. Remember that we have to select the minimum cost. So we are not going to use this path. We are not going to use this path to go to n3. Rather we are going to use this path. So if I go back, I'm going to create a table at node 1 directory. So my destination node is n3 and the next node where I should go to reach to n3 is n4. It's not directly I can land to n3. Next is if I want to go to n5, right? So from n5 also, if you see over here, I need to check the route from n5 because if you see, this is the minimum cost from all the three if I select. Alright, let me just use the eraser to erase it all. Alright, now if you see over here, going from n1 to n5, right? So going from n1 to n5, let's check what is the minimum cost. I can go from n2, but this has a cost of 2. I can go from n3, it has a cost of 5. I can go from n4, it has a cost of 1. So I will select this path. Now from n4 to n5, there is a direct link, so I will choose this path. So in the table, what will I store? Going to n5, the next node where I should send my packet is n4. Same thing goes for the n6 also. I will choose n4 because of the obvious reason, because it has the minimum cost. n4 to n5, so my next station is n4. Same is for the n6 also. Now coming to the node 2 directory. Let's talk about node 2 directory. Now from node 1, from node 2, I can go to node 1 also. All right. From node 2, let me just erase all this. Now we are talking about how to maintain a directory on node n2. Now if from node n2 to my next destination station is n1. If I want to go to n1, so either I can go from n1. So what can I do? Either I can go from n2 to n1, which has a cost of 3. Either I can go from n2 to n4, which has a cost of 2. But I may not choose this because I will choose this, I may not, here, for example, if I choose this one from n2 to n4, it has a cost of 2. Then I will check what is the cost from n4 to n1. Since this is 7, 7 plus 2 is 9, so I may not select it. Going from n2 to n1 directly gives me a least cost. So, in the directory, destination is 1, next node is 1. Now from going from node 2 to node 3, I can go from here. I can go from here also, from n2 to n4, but same reason, if you see over here, going from n2 to n4, I have a cost of 2. And then from n4 to n3, I have a cost of 3. So 2 plus 3 is 5, but here it is 3. So in the next hop, what I will write? 3. Same thing I will do for going from n2 to n4. I have a cost of 2. Let me just erase the ring. Alright, I have a cost of 2. I can go from n1 to n4 also, but if you see, going from n2 to n1 already has a cost of 3, which is more than my direct link. So I will, so my destination is 4 and the next node where I should send my packet is 4. Now going from n2 to n5, either I can go from n3, so let's check it, but I will select the minimum cost, n3 and n4, so even n1 also, because these two are the same cost, but this is the minimum cost, so I will choose this one. So n2 to n4 is 2 and n4 to n5 is 1. So the total cost from reaching from n2 to n5 is 3 and the next node is 4. If you see, the node is 4. Then from node 2 to 6, again it is the 7. Same thing we are going to do for the node 3, node 4, node 5 and node 6 directory. So once each node has completed making their directory, then a centralized directory will be made by copying all this. So if you see, from node 1 to 1 there is no cost. From node 1 to 2 the next node is 2. From node 1 to 3 the next node is 4. From node 1 to 4 the next node is 4. From node 1 to 5 the next node is 4. From node 1 to 6 the next node is 4. Same thing, I go to node 2. From node 2 to 1 the next node is 1. So we are just going to copy over here a central routing directory. All the individual directories will be copied in the central routing directory. So this is how each node makes a routing table. This is called as the fixed routing table. So it will be fixed. Now if there is some change in the topology, if the link breaks, then the same thing has to be done over and over again. So this strategy is quite a simple strategy, but this is not a flexible strategy. Why? Because it cannot tolerate the dynamic changing nature of the routes in the network. So that's why it's not a quite flexible strategy. So this was very simple. This was about the fixed routing, how the each individual nodes makes its routing table, and then a central routing table is made at some central node. The next routing strategy that we are going to talk about is flooding. Alright, so let's talk about flooding now. Now, flooding, as the name suggests, it floods the network with a copy of the packets. So in case of, it's another simple routing technique. This technique requires network information whatsoever, and it works as follows. Packet is sent by a node to every neighbor, to every one of its neighbor. So eventually multiple copies will arrive at the destination, or multiple packets will arrive at the destination. No network information is required, and each packet is uniquely numbered, so duplicates can be discarded. It needs to limit the continuous retransmission of the packets, because node can remember the identity of the packets retransmitted, and when the duplicate copies arrive, they are discarded, and it can include a hop count also. So what it does, a packet is sent by a source node to every one of its neighbor, and at each node incoming packet is retransmitted on all outgoing links except from where it is arrived. So this is how this techniques work. Let's understand by an example. Alright, so here we have an example over here. Alright, so let's talk about this example. So for example, in this node, same thing, we want to send a packet from node 1 to node 6. So if a node has a packet to send to node 6, now first of all, in the first hop, it will send a copy of the packet to its neighboring nodes. Now the neighboring nodes of the nodes to which one is attached. It is attached to 2, it is attached to 4, and it is attached to 3. So it will send a copy of the packet to nodes 2, 3 and 4. So it will send over here to the nodes 2, 3 and 4. Now in the second hop, now node 2 receives a copy, node 4 receives a copy, and node 3 receives a copy. So now node 2 will send the copy to node 3, and node 4, it will not send a copy to node 1. It will not, nodes will not send a copy to the link from where a copy is received. Rather, they will send a packet to the other nodes. Similarly, node 4 will send a copy of the packet to node 2, to node 3 and to node 5. And similarly, node 3 will send a copy of the packet to node 2, to node 4, to node 5 and to node 6, and so it goes on. Eventually, a number of copies of packet will arrive at node 6. So the packet must have some unique identifier, for example source node or the sequence number, so that node 6 knows how to discard all but the first copy. Now, unless something is done to stop this retransmission of packets, the number of packets in the circulation, they grows without any bound. And the one way to prevent of growing or flooding the network with such a large number of packets is to identify those packets which have been already transmitted. So if you see in the third hop, the number of packets, each node would retransmitted whatever message they have received except to the sender node. So for example, node 2 has received from 3. It will not send the packet to node 3, rather it will send it to all except node 3. It will send the packet to node 1, it will send the packet to node 4. So if you see this way, the number of packets will flood the network, it will grow. So there should be some identifier to stop this growing of packet. And a simpler technique is to include a hop count field. This can be originally sent to some maximum value, and each time a node passes the packet, the hop count can be decremented by 1. Alright, so the properties of the flooding, it has four remarkable properties. First thing is, all possible routes between the source and the destination are tried. So it's highly robust and it can be used to send the emergency messages also. So no matter what link or node outage have occurred, a packet will always arrive at the destination if any of the path exists. At least one packet will have taken minimum hop route. So because all routes are tried, so at least one copy of the packet will arrive at the destination that have used the minimum hop route. Nodes, directly or indirectly, they are connected to the source are visited. So all nodes that are directly or indirectly connected to the source node, they are visited. And the disadvantage is high load traffic is generated, and sometimes there are the security concerns. So because of the first property, it's highly robust and it can be used to send emergency message also. But and the second property suggests that it can be used to set up a route for a virtual circuit network also. And based on the third property, it can be useful for sending some important information to all the nodes. But the disadvantage is high load, and sometimes there are the concerns for the security also. Alright, going to the next slide. The third routing strategy for today's lecture is random routing. Now, what is random routing? So the random routing, random routing has the simplicity and robustness of flooding with less amount of traffic. So with random routing, a node selects only one outgoing path for the retransmission of the incoming packet, and the selection can be random or round robin. Random means any one link can be selected. Round robin means first, if there are 4 links, first this link is selected, then second this link is selected, then third this link. Then for the fourth packet, the first link will be selected, then for the fifth packet, second link will be selected, and so on. This is called as the round robin. Now, if all links are equally likely to be chosen, then round robin will be selected. But a refinement of this technique is to assign a probability function to each outgoing link, and then to select the link based on the probability. So probability calculation is done based on the data ring or the fixed link cost. Then the sum is taken over the outgoing links, and it actually provides a good traffic distribution. Like flooding or random routing techniques, this type of technique requires no network information. Now, because the route taken is random, the actual route will typically be, it can neither be a least cost route nor it can be a minimum hop route. So, but the network must carry a higher than the optimum traffic load, although not nearly as high as flooding. So it is actually a random routing performs better than the flooding also. So the last one is adaptive routing. We are going to discuss this adaptive routing in the next lecture in the next week, and this is for all this week. So thank you so much.